Welcome. This is March 10th, EE380, 2010. I think it's the last lecture of the quarter. So please, if you're taking the class for credit, please do course evaluations. If you're trying to graduate this quarter, historically we've turned in grades faster for people who have submitted who have done the course evaluation than for people who haven't. Also, as I said at the beginning of the quarter, we typically don't do incompletes because we've discovered that people who take incompletes never finish. And I know you're a special duckling, but you're not going to be different either. Sorry about that. So please catch up and do the lectures by the end of Dead Week. So that's that. It's sort of interesting that operating systems and instruction sets have converged. There's not a lot of diversity there anymore, but programming languages have not.
They have diverged?
Well, they wax and they wane. I mean, for a while, Java was going to be it. Well, programming languages come into being because someone decides that there's a better way to express solutions for something that they care about. And in this case, and in this, small size is a huge benefit because it makes it possible to try and reap these advantages. It also, but it has a cost that it can make it harder to express what you actually need to get things done. Entrenched languages, Java, have huge libraries, huge numbers of libraries to do supposedly everything you need. Lua is one of the few languages to successfully address these issues and to actually become successful. Roberto Jeruzalemski is here to tell us how he managed to pull this off.
Well, thank you. I'll start the talk with a very broad discussion about design of programming language, mostly to warm up. I'm not going to say anything very bright about design of languages in general. Then I'll talk a little about Lua in general, just an overview for those that don't know the language. And then I'll try to address some specific points in the design of Lua that I think are interesting and I think that show more or less illustrate the kind of approach we have for designing the language. I think this last part will be the most important part of the talk. So in general, I think when you're designing a language, as in any other design, there is a lot of trade-offs. You must choose between different requirements, between different important things you have to do. And in programming languages in particular, designers seldom talk about these trade-offs. There is this myth of the general programming language since I think it was created by PL1. And since then, most languages at least are presented as they are good for everything. It's difficult for one to come out and say, this language is specifically created for this particular niche or for this part. Of course, you can use a language for everything, for anything. People use Java for numeric computation, for instance. But it's difficult to say, okay, this language is good for that. It's not, you can use that for anything, but it's not particularly good for that, and it is particularly good for that. Lua is not good for numerical computations, for instance. So some typical trade-offs, we have security versus flexibility. For instance, to have good security, you need static verification, static typing, and of course any algorithm of static typing will rule out valid programs that you can be, it's a discussion whether they are well designed or not, but there are a lot of valid programs that any static system you have to rule out. This is theoretically impossible to accept anything that is valid. Another typical trade-off is readability versus conciseness. This is a long time discussion since APL. Now with Perl, Perl is another example that it's very concise, very good to write code quickly, but it's very difficult to read afterwards, and it's difficult for non-programmers to understand or even to program in that language. Another trade-off is performance versus abstraction. The more levels abstractions you have, usually it's more difficult to get performance. This is particularly true in an interpreted language. That's also a trade-off between compile time and run time. That sometimes people say, of course, you must sacrifice compile time when you need run time, but sometimes some systems, for instance, just yesterday we were discussing this, some games take some 10 minutes to link the game. So they just want to change a speech for a character, and then they must wait 10 minutes to see how the character reacts to this new speech, or just change some movement. So not always you want to sacrifice compile time for runtime. So this is another typical trade-off we have. And there is a special trade-off that is simplicity. Because most other conflicts we can solve by adding complexity to the language. Not all of them, but a lot of them you can solve by adding complexity. For instance, conciseness versus readability. You can have different ways to write the same thing. You can write in a short form, the language presents it in a longer form. There's a lot of different things that can be solved. You can have smarter algorithms to solve performance problems, but all that add complexity to your system. So if you want a simple system, then this is a trade-off against almost all other features. So this is. And then comes Lua, which is a scripting language that has simplicity as one of its main goals. Its small size too. It's simplicity, of course, not the same thing as small size, but there is a good correlation between the 2 points. And Lua is also what we call a real language. There is the codes, or what you can discuss what is a real language. But the point is that we have many users, we have many uses. So we need a real balance between the famous as simple as possible, but not simpler. I mean, of course, you can create something very simple. Lambda calculus is very simple. Turing machines are very simple, but they are not useful. So C++, on the other side, at least one of the original books of C++ claimed that C++ was as simple as possible, but not simpler. Yeah, that was the first time I saw this. Yeah, exactly. So this is exactly the kind of trade-off, what you mean by not simpler and as possible. So it depends on. So Lua also is not as simple as possible. There is a in scale here from as simple as possible to but not simpler, and depends of the interpretation of these different words where you stop in this scale. Well, so for those of you that don't know about Lua, as I said, Lua has a lot of uses. Lua is particularly popular in games. Just yesterday we have a whole day tutorial in the Game Developer Conference in San Francisco, and it ends with a panel that the title of the panel was, "Is Lua the ultimate game scripting language?" And the answer was more or less, currently yes. I mean, and actually in several polls show Lua as the most popular, almost more than half of the games that use a scripting language use Lua as its scripting language. But Lua is not used only in games. A very popular use of Lua is embedded devices. For instance, so Canon has Lua embedded in some cameras. Logitech has Lua embedded in some keyboards. Olivetti and Océ has Lua embedded in some printers. And there are several robots, and there's all kinds of devices that have Lua. There is a version of Lua for the Lego Mindstorm that runs, that's not distributed by Lego, but so a lot of uses of Lua in embedded devices. And of course in scripting, the embedding in applications, not in hardware but in software. So for instance, the big trio of network security, the three of them, Wireshark, Snort, and Nmap, all of them use offer Lua as a scripting facility to script the different tasks. And there are other uses. Adobe has the second version of the Lightroom Photoshop. Is more than half of it written in Lua. This is not a typical example. It's not exactly scripting. Then they are using Lua as a real programming language. But there are many other applications. So what's the main goals of Lua? As, of course, simplicity and small size is the main topic that we are going to talk about here. But there are other important goals of Lua that make Lua popular for those uses that I talked about. The other one is portability, and the other one is embeddability, which is, I put there scripting. Currently, the word scripting language is meaning its original, it's losing its original meaning. Because in the old days, scripting means to control some application, was kind of a language to control programs or other programs like the shell or pieces of programs written in a different language or something completely different of the program itself. And nowadays, people use scripting language as the same thing as a dynamic language. So, for instance, everybody say Python is a scripting language or Perl is a scripting language. They are not scripting language. They are very good dynamic languages. But they were not intended for scripting. They are not used to control. Usually when you write a program in Python, you write the whole program in Python. And you write a program in Perl, you write the whole program in Perl. While all those examples I gave in the other slide, you have a good part written, sometimes a good part, sometimes not as good part written in Lua, and a good part written in another language, and Lua exactly is scripting these other parts of the program. So Lua, since the beginning, was created focusing on scripting, in real scripting, that we call sometimes embeddability, the facility to put Lua inside some other program to control that program. So about small size, here is the evolution of source lines of code in of the Lua implementation along its different versions and time. So we see we started here in '93 with less than 6,000 lines of code. Currently, Lua is much bigger than it was. That's not simpler than that. But still, we are still less than 18,000 lines of code for a complete, this is the complete language with the libraries, everything you need to install. This is still quite small for, if you compare to almost anything similar. So this, as I say, this is not the same as simplicity, but it's more or less a proxy for that. We'll discuss simplicity later. Portability, Lua runs in almost anything we've ever heard about. Of course, it runs in, most people say, oh, it's portable. It runs in Unix and Windows. And so it's portable. Lua runs in Unix, Windows, in Symbian, in the Nintendo DS, in PlayStation Portable, PlayStation 3. Both, that was, people were talking about yesterday, both in the cell processor. Lua runs both in the PPE and the SPE. There are those coprocessors. There is very small footprint. They have some 250K of memory, something like that, each of them. And people at Sony are putting Lua running inside the SPE. Lua runs in the Android, the iPhone, and I mean almost anything you, and as I said, in several devices, small devices, robots, printers, cameras, etc. And the important point about portability in Lua is that most of that portability doesn't come from a lot of different if-else for different systems. It's not that, oh, I want to port Lua for that device, so I'm going to put a lot of different if I am in that device, then define this as this. Most of the source code is exactly the same for all these devices. We stick to the standard. We are really, I think one of the things I learned most during all the time I was developing Lua was the C standard, and you are really stick to it, and it's and even when we follow the standard, we avoid the dark corners of the standard. We know there are some things that the standard says it should be done that way, but we know that some compilers do not follow that, so we avoid that kind of thing. So Lua is really very, very portable. The people usually talk about half an hour to put Lua running in a completely new system, or 2 hours when the system is completely unusual. And the embeddability, as I say, is also a very important point in the design of Lua. Lua is provided as a library. I'll talk about that later more. The API between Lua and C, it's a very important point in the design. It tries to be a simple API that uses simple types, it uses low-level operations, and here is a very nice example of embeddability. Lua has been used, real use, embedded, of course, in C++. This is the official API, but people has adapted Lua to be used also with Java, with Fortran. Fortran is not in use anymore, but we did use Lua controlling Fortran programs. C#, Perl, this is very strange, but it's real. I have real, Python, for instance, someone related to me, a real case, the bank has a huge application, a financial application written in Python, and they wanted to script that application, but they didn't want to allow the scripter to go inside the program, to change things inside the program. They wanted a sandbox between the script, and Python doesn't provide facilities for that, so they offer the script in Lua, so it's a different language, so they have a very clear API between Lua and Python. And Perl, for instance, the CPUN, the official Perl repository, they have a module for scripting Perl programs with Lua, so Lua is really used for scripting all those different languages. This is not a... Ada is the only one that is not. I don't think anyone uses Ada, so nobody would use Lua to script Ada, but this is just, I mean, has been done, but I don't think anybody used that. But the other ones, all of them have some real use, someone out there using that, trying to...
Did you fly on a jet to get up here, or did you take a ship?
Pardon me?
Fly on a jet to get up here, or did you come here on a ship?
Fly.
If you flew, you were flying on Ada.
Oh, yeah. You're using Ada there? Oh.
Boeing uses it.
Well, then I hope they are not using Lua to script that. I already said that I've never board a plane that has Lua embedded. No. As I said, Lua has different priorities. So let's have a look at how is Lua. This is, as I said, is a very general overview, just a little taste of the language. Lua has a very conventional syntax, somewhat verbose. We have explicit ends for all constructs. So here is a recursive factorial function. Here is a loop version of the factorial function. You see there is no type declarations, there is all dynamic typing. So if n is equal 0, then return none. Well, I think it can understand most of this. This is just to have a general look. Semantically, Lua is quite similar to Scheme. Most people don't realize that, but it's similar to the first way of... One reason is because both, I think, favor simplicity. The other is that we took a lot of inspiration from Scheme along the time. So, for instance, Lua is dynamically typed. The variables don't have types, only values have types. Functions are first-class values with static scoping, so we can do functional programming in Lua. For instance, here, those declarations of function we saw in the other slide, they are in fact just synthetic sugar for what is really going on is that. So you're actually creating an anonymous function and assigning it to a variable, exactly like in Scheme. When you define a function, you're creating a lambda, and the define is a macro that expands to a lambda and assigns. Lua is also proper tail recursive. Lua does not have full continuations. I mean, here it's wrong. It's not, it's not full continuations that I meant. It doesn't have multi-shot continuations, but it does have one-shot continuations in the form of coroutines. I'll talk more about that too later. So now let's talk about specific points in the design of Lua. We will talk a little about tables, coroutines, and the API between Lua and C. So tables in Lua, table is the name that Lua gives for associative arrays, that it associates any kind of value to any key, not only strings. The keys can be not only strings, but can be numbers, can be strings, can be functions, can be any value in the language, and the values themselves also can be any value. So you can associate functions to their names, you can associate names to functions, you can associate functions to other functions, tables to tables, whatever to whatever. And is the only data structure mechanism in Lua. This is, some people say this is the most distinctive aspect of Lua, that Lua has only, a lot of languages offer tables, offer associative arrays, but in most of these languages, associative arrays is something else. You have arrays, you have records, or you have a lot of things, and you have associative arrays. In Lua, you only have associative arrays. You should do everything you need to do with them. So why tables? Actually, one of the inspirations for tables in Lua came from VDM, Vienna Definition Method. In VDM, we have three types of what they call collections. We have maps that are equivalent to tables. We have sequences, and we have sets, finite sets. And of course, mathematically or even computationally, you can represent any of them with the other. You can choose, oh, my language only has sequences, and then I will represent sets using sequence. I will represent maps. This is more or less what Lisp does. I mean, it did in the beginning. Then they gave up and introduced arrays, but. Yes, because exactly the problem is that although you can represent anyone with the other, I think that map is the only one that you can represent the others, both in a simple way and efficient way. You can't, for instance, you can represent sets with sequences, but either you have a simple implementation, with just a linear list, or you have some complex, but then it's not efficient, or you have something efficient which is not simple. To have both, but we see that with tables, with maps, you can have both simple and efficient implementation, assuming, of course, that the implementation of maps is efficient. So let's see, as I say, we can put most data structures in tables. So records is just a matter of syntactic sugar. We write t.x. It means index the table t with the string x. So it's just that, syntactic sugar. So we can create that syntax here, creates an empty table, and then you create a key x associated to 10, a key y associated to 20. You can access them. This is exactly the same as this. It's just syntactic sugar. The compiler translates that to that. What is run in runtime is that part. Arrays, you just have to use integers as indices. For instance, you create an empty table and then you run a loop for y from 1 to n, assigning 0 to a of y, so you create, this is an array. In particular, the implementation of tables in Lua is not that simple. Lua has some special algorithms. For instance, if you create a table like that, Lua internally will recognize that you are using the table as an array and will represent it internally as an array. So a table has two parts. It has a hash part and an array part. and the algorithm automatically chooses the size of those and how to distribute the entries between them. Sets is also very easy to represent. Just use the indices to store the elements. So you create here an empty set. To insert an element in the set, you just say that its value is true. To test whether an element is in the set, you just test whether there is a value associated to that index. And to remove, you just associate mu to that. So it's very easy to. So as I say, it's very easy to represent all those structures in tables, and assuming that the underlying implementation of tables is efficient, these are very efficient too. In Lua, tables go behind simple data structures, and we use tables for everything. So even modules, or what we call modules in Lua, are tables, and objects are also tables. In that example, we have a module math with a function sign. Math is just a table, and inside it has the key sign associated with a function, and so math.sign there, the dot is exactly the syntax sugar we saw before. There is nothing new here. For objects, we need a little more than that, so we have, I will show you now, you need some extra synthetic sugar and some delegation mechanism. So it's not only the basic tables, but it's very little you have to add to the language to have an object system. So the first step is the synthetic sugar, because when you have first-class functions and tables, you almost have objects. I mean, you have tables are objects. You can have methods attached to them because you can have functions on those objects. But one of the problems is that a function inside the table doesn't know that it is inside the table, so it doesn't have access to other fields on that table. So this synthetic sugar solves this problem. You can create a function with this column syntax, a colon foo, and it translates to create a function in that table with an extra argument self. It produces, so inside the function you access the instance variables as self.x or self. Because self will refer to the table where the function is running. And to call the function, you have a correspondent syntactic sugar that is a colon foo. It just translates to get the full function of a and provides the receiver as an extra argument, so that argument will come here to this self and everything close. But you still have the problem that each object needs to have all its functions inside the table. So you have 1 million points. Each point has the x, the y, and all the operations of a point. So that's not very good. So we have also a mechanism for delegation. But delegation in Lua, it's quite different from other inheritance mechanisms, because it is defined in terms of tables, not in terms of objects or methods. What you delegate is a table access. That's all it does. So if A delegates to B, it means that any time you try to access a field in A and the field is not there, then Lua will automatically tries to find that field in B. So the delegation is about accesses, table accesses, and not anything about methods or anything related to object-oriented designs. But that allows prototype-based and class-based objects. Here we see an example. Suppose we have an object A, and it delegates to an object class. And then I write a colon foo of x. That is translated, this is just synthetic sugar, it becomes a.foo of ax. Then Lua tries to get foo in table A doesn't have a table foo, so it goes to class. Class does have a table index foo, so the result of this expression a.foo is that function. So that function got called with the A as itself. the self of the function. So everything works as expected. Okay? So that's all. If you want to do subclasses, you just use the class to delegate to another class. So if foo is not there, it's going to get that in another point. Actually, there is a sure.
Functionality in 5.1?
Pardon me?
Is this in 5.1?
No,
No.
it's since, I
It's been
mean,
there, this syntactic sugar's been there for a while.
yes, the column, the syntactic sugar is been,
The delegate.
the idea of delegation has been since version 2.2 or 2.1, but in different forms. I'm not showing the details how you, this is called meta tables, is the scheme how you do the, yes, here are just a simplification of the details of how you do A to delegate to B. But the idea of delegation is, since it has changed a lot, the details.
Yeah,
but
now
yes.
it's a metatables. Like,
Yes, okay, yes. And this is an important detail, that the delegate actually, may, instead of being a table, it can actually be a function, and then what Lua does is, when you access a field, and the field is not present, then Lua calls that function to provide that field. So you can do whatever you want in any table access with that. Of course, it's more expensive than this direct form of delegation, but it's much more flexible too. So what's the problems with tables? I mean, tables are very good, but of course there is a lot of problems. One of the main problems is that the implementation of any concept with tables is not as good as one that is primitively supported by the language. For instance, objects, we do not have access control, we do not have private or protected fields, anything it's in the table, anyone can access that. There is a detail that it's quite annoying about the length in sequences. As a sequence is just you associate numbers to values, but where it stops, I mean, if you do not have holes, you can say, okay, the first absent field, it's where it stops. But if you want to have nils, holes inside the table, this is a kind of a never-ending discussion. What is, so there is, of course, you have sequences, primitives, you would not have these problems. And another problem is, this is more unexpected, is that different implementations confound programmers. For instance, what happens in Lua is do-it-yourself object systems. Each programmer has its own way to implement objects. Sometimes even the same programmer has different ways to implement objects in each different program he writes, or each different module he writes. That's, I mean, everything works fine, but people, every time people start reading a program, what's an object here, what's in a class, it's not very, some people joke that Lua is that kind of thing. You want to get bread, you just go to the farm and just you plant your wheat, and then you get that you must grow up everything from the ground up. So it's good, it gives a lot of flexibility, but sometimes you just want to have things done fastly, and then you have to, what object system am I going to use? Do I need single inheritance, multiple inheritance, etc.? So let's talk now about coroutines. Coroutines is also a very important concept in Lua. Gamers love coroutines. Coroutines is a very old and well-established, more or less well-established concept, because exactly, although everybody knows what is a coroutine, there is a lot of variations of what people understand as a coroutine. And these variations are important. They have, I mean, they are not just details. Some of these variations change completely the expression power of coroutines. In particular, Lua, coroutines as implemented in Lua are equivalent to one-shot continuations. And coroutines as implemented in most other languages are not equivalent. I mean, they are less expressive than one-shot continuations. Well, here's just a quick look at how are coroutines in Lua. We have three main functions. You have create, that you give any function as the body of the coroutine. and it creates a coroutine called C. It doesn't run when you create the coroutine, it just stands there. And then you have a function resume that starts or resumes the coroutine. So for instance, when you call resume first, it starts executing the function, prints 1, and then it yields, it stops, suspends the execution. When you resume again, it continues for where it stopped until the next yield or until the next end. So this is very basic. What is special about coroutines in Lua? The first point is that coroutines are first-class values. So that C that coroutine creates, the coroutine creates, is a first-class value. You can pass it around the program, and most importantly, you can resume it from any point in your program. You can escape where it was created. You can do whatever you want with that C. You can call it, resume it whenever you want. The second important point is that coroutines are what we call stackful, which means that it can yield inside any number of function calls. In that example, it yields from inside the main function, but the important point is that function that you resume can call another function that calls another one, and then you have any levels of nesting in your stack, and then you yield, and when you resume, you are back there to continue execution and to return, etc. That in implementation terms, it means that each coroutine has its own stack. And the third point, this is not as important, although in Lua it is important, is that in Lua coroutines are asymmetrical. So instead of a transfer, that just one function to transfer control, like in Modular 2, you have transfer. In Lua you have resume and yield as different functions. The main difference here, this is very subtle, but the transfer is more or less equivalent to full continuations.
So are all variables global? And what kind of parameter passing are you doing between routines? Is it traditional call by reference or call by value?
It's called, well, in Lua you have the same thing as scheme. You have call by value, but some values are references. Because tables, for instance, a variable is always a reference to a table. So when you pass a table, you're always passing a reference. And in coroutines, you have global variables, but you have local variables. And I haven't talked about that, but you can pass arguments both in yield and resume. In resume, you can pass arguments that are the results of yield. And in yield, you can pass arguments that become the result of the resume. So you can pass arguments in both directions. So, but you may have global variables that are accessible for among all routines.
Local, non-global, which will disappear when you exit.
Pardon me?
When you exit a routine, that you will have some local variables that have no value after you exit, right?
That happens with any function.
Yeah.
Yes, unless the variable may escape because of lexical scoping. So you may have a function with a variable. Inside it there is another function that accesses that variable, and the function exits. But if this function escaped and it's stored somewhere else, the variable still exists because this function can access it. So this is the whole story about lexical scoping. Oops, sorry. So, what's good about coroutines? The first thing about coroutines is that it has a very simple and efficient implementation. The implementation of coroutines is the easy part of multi-threading. Just each coroutine is a stack, and to change between coroutines, you just change a stack you're running. There is no synchronization problems. That's why it's the easy part. You just have to manage the stacks. The point of being first class and stackful make coroutines what we call complete coroutines, which are the ones, as I say, which are equivalent to one-shot continuations. Actually, we can write a function call 1cc in Lua in terms of coroutines. You can to have a library that has a function that does exactly what you expect from call1cc, that you calls a function giving as argument a continuation that you can call it once. But although it is equivalent to one-shot continuations, Colloquium presents them in a format that is much more natural to most programmers. I mean, they are procedural. They have most programmers have this idea of sequential programming. Okay, you stop, then you resume from that point. It's much easier for them to understand, not all of them, but for most of them, to understand the concept of continuations, what is a continuation, what it means to call the continuation just once, etc. So it's much more natural for. And of course, most of the common uses of continuations can be coded with coroutines. One of the main uses of continuations are coroutines, so of course this will use, it's easy. And most uses of both continuations and coroutines is related with who has the main loop problem. Now you have, for instance, in the producer-consumer is a typical example. You have a producer, which is a loop. You have the consumer, which is a loop, and how do you structure your program so that both loops think they are the main loop and how they communicate. Also, in scripting language, a typical problem is that of extending versus embedding, which means that the main loop is in the host language in C, or if the main loop is in Lua. And again, with coroutines, you have both. You can have both thinking they have the main. I mean, you can have C calls Lua. Lua now has a main loop, but that main loop yields, though it goes back to C, and C loops, and both things they are controlling the other, so you don't have this problem of, oh, this one is the main one, or this one is the other main one. Of course, this is a famous problem, the same French problem of you have iterators versus generators. Iterators meaning you give a function and then execute that function in all elements of your collection, and generators mean give me the next element of the collection. So again, is a problem whether the main loop is inside the collection or whether the main loop is outside the collection. With coroutines, if you have an iterator, you just give yield as the function to be executed over all elements, and then you are outside that loop. So it solves a lot of different problems. And of course, it's very easy to implement collaborative multi-threading with coroutines. You have any operation that may block yields, and then you have a very small scheduler that runs across all coroutines, resuming them, and it's very easy to implement that. Of course, coroutines are not as good as real continuations. There are some uses of multi-shot continuations that cannot be expressed as coroutines. A typical example are Oracle functions. Oracle functions is the idea of you want to implement a non-deterministic algorithm. You can just write if Oracle, then tarara, else tarara. With multi-shot continuations, you can capture the continuation inside the Oracle, and then returns that with one value, and then if something fails, then you return again that with a different value. This is a very interesting programming technique that you can do with multi-shot continuations, but if you want to do that with coroutines, you have to change the structure of your program a little, or much, depends. So let's talk now a little about the Lua C API. As I said before, Lua is a library. What that means, I mean, formally, Lua would be an abstract data type. I mean, if you want to formalize Lua, the important, but what is Lua? Lua is a huge abstract data type. You has a library, you open this state, and you do a lot of operations over the state. You create values, you create different things there. The API has 79 functions, and what we call the language itself is actually the parameter to one specific operation over that abstract data type, that is the function load, that gets a string with source code and transforms that into a function inside that abstract that data type, that when you call the function, you have side effects on that data type. So that's the real point of view of Lua. Although everybody thinks of Lua about a language, it's really, and as I said, this is not something that later, oh, Lua, it's good, let's try to make an API to access that. Since day one, we thought about Lua in those terms. Maybe not as clear as here, but I mean, the API was always a central part of the design. So how is this API in Lua? This has evolved a lot along the years. Most API, one of the main problems in the API between API to scripting languages is the problem of garbage collection and the problem of dynamic typing. Because for dynamic type, so the problem of dynamic typing, most APIs use some kind of value type, some kind of union. For instance, in Python, you have the Py object. In the Java native interface, you have a J object. That is something, some value, some magic value in C that can represent any value of your host language. Of course, Java is not dynamically typed, but from the point of view of C, it is dynamic because it's an independent type system. So when you call a function, when you do anything in Java from C, you don't know what types are expected. So one main problem of this kind of value type, as I say, is garbage collection. Because there is no way for the garbage collector of the scripting language to know about the existence of these values in C. So once there are different solutions, Ruby, for instance, has a very dirty solution, but it just goes across the C stack and doing a conservative collection. I mean, whatever looks like a pointer should be a pointer. So it's not portable at all, and it's not very elegant, but it works. In Python, you have explicit manipulation of reference count. So if you want to preserve an object, you have to increment its counter. If you want to release an object, you have to decrement that counter. And in Java, you have two different kinds of reference. You have local references that are automatically released when the function ends. And you have global reference. You can get a local reference and call a function that transforms that into a global reference, and that will be preserved until you destroy that global reference. Of course, both forms, it's too easy to create dangling references and memory leaks. It's too easy to get, in Python, it's too easy to forget both to increment the counter or to decrement the counter. With one, you create dangling reference. With the other, you create memory leaks. In Java, it's very easy to get a lock because it's worse because the type is the same. Both types of local and global reference is a J object. So it's very easy to forget and store a J object as a permanent object without transforming it into a global reference. Oops, sorry. I should have removed it. And so how Lua solves this problem? In Lua, we do not have a Lua object type. Instead, all Lua objects live inside Lua. We do not have Lua objects living in C. There is no type in C to represent Lua objects. What we have is two structures that keep the objects that C is using. One is the stack, the main one. The other is the registry. We'll talk about the stack, which is the most important one. So every time any function that it's working with Lua, it has access to an abstract stack that keeps every object the function is using, it's kept in this stack. So we have injection functions. When you want to convert a C value into a Lua value, you provide the C value and it creates that object on the stack. It just pushes that new value into the stack. And the projection functions get values from the stack and transform them to C values. So all values are all in this all the time in the stack. You do not have, so if the object is in the stack, of course, it cannot be collected by the garbage collector. When the function ends, the stack is erased, so everything that is in the stack is automatically destroyed. So let's hear just a short example how you, for instance, how from Lua you can call, from C you can call a Lua function. Suppose you are in C, you want to call f of hello and 4.5. You just get the function, Lua get global, gets the value of the global f, and pushes that value into the stack, whatever that value is. Because functions are first-class values, they are just pushed as any other value into the stack. Then you push the arguments. These are the injection functions. You are injecting a string, hello, a C string. It becomes a Lua string into the stack. And then you have a C number. It becomes a Lua number into the stack. And then you have just call. I forgot to mention, this first argument here, L, it's the state you are working with. In Lua, there are no global variables from the C point of view. So everything you do is in a specific state that you must create before anything. You can have multiple states, for instance. And so you must provide the state, say, doing all that in this particular state. So call L. The 2 is the number of arguments. So it knows that everything, all those n arguments in the stack are to be provided to the function, and the value just behind those values is the function itself. And this is the number of results. In Lua, a function may return more than one result. In that case, we just want one result. So this call will run the function, will remove all those values from the stack, and will push the result of the function in the stack. And then we have the projection functions. We can check. -1 refers to the top of the stack. We can index the stack from the top or from the bottom with positive and negative values. So we check whether if the top of the stack is a number, we just get that number and print the corresponding value.
So if f hadn't been a function, what would that call? What would Lua call?
In that particular case, if f is not a function, then that would raise an error. We use long jumps, so that will be error is supposed to be handled somewhere in another place. Yes, yes. Now, here you are in C. So in another C, you suppose the C called Lua, and Lua called that, and then you are back to that C original part. But you have a P call, there is a protected call, and in that case, it protects any error. It just returns an error code. Yes, exactly. So it returns an error code here, it checks the error code. If there is any error, the error message is on top of the stack. It doesn't print anything. Lua never uses prints or anything from the operating system. It gives you the error message and you do what you want to do with it. So here's another example how you call a C function from Lua now. So that's how you augment Lua with functions written in C. So you have a square root function. All functions should have this signature with a Lua state, that is what state that function is going to use, and it returns an int that we are going to talk about shortly. So what the function does, it receives the argument in the stack. So it gets the argument in the stack. So this is an auxiliary function. Check number, it checks whether the value at the index 1 in the stack is a number. That function exactly, if it's not a number, it raises an error directly, so you don't have to worry about that. And returns the corresponding number. Then you do the computation. In that case, the computation is just to do the square root. And you push the results back into the stack. In that case, that you push that number. And as I say, because Lua functions both C and Lua functions may return more than one result, you return here the number of results this function is returning in the stack. That means the last element is the stack, is the value of this function. An important point here, a detail, but is that notice that here, this L here means Lua library. This is an auxiliary library with extra functions. That function is not part of the official API. It's done on top of the official API. So it uses that Lua get number, Lua is number to check whether there is a number. It uses a function Lua error to throw the error. So this is all built on top of, so that keeps the kernel of the language small, and this, you have these auxiliary functions, but they are completely separated from the kernel. The kernel is really simple. It doesn't provide that kind of very high-level function. Oops, what happens here? Should do something. Where I was. Well, there's something wrong with my presentation. I'm sorry about that. Here it works. I'll try here. What is going on? There is something marked in the last slide, probably. Where should I? I think it's easier to present in this form because it's almost at the end. It doesn't. It's too much work too. So let's finish this form. Sorry about that. So, how do you do if you want to preserve an object between different C functions? As I say, everything that is in the stack is erased automatically when the function ends. If you want to preserve something, Lua does not offer anything special. It just offers one fixed table in the API. You have access to the table that is called the registry, and it's a regular Lua table. And so if you want to do a global reference, as it's named in Java, you just put the object into the table and get any index you want and stores the index, and then whenever you want, you go to that table and retrieves the element from there. Of course, you still, the problem of memory leaks is still present. This is something, I mean, it's not exactly memory leaks, it's memory leaks from the program point of view, not the implementation point of view. Of course, this is something that you cannot solve. If someone puts something in the registry and never removes from that, there is no way you can solve that. But for instance, you can traverse the registry and find what's going on, what it's consuming memory, because it's everything in official Lua structures. And there is no way to have memory leaks. Memory leaks is mostly impossible if you do things with the C API. So what's the problems with the Lua C API? One main problem is that too low level, because as I say, for instance, that operation to check the type of an argument is already something done on top of the primitive operations. The problem that is stack-oriented sometimes is confusing for many people, I mean for almost anyone. Sometimes what is where? Oh, in the index 2 I have the function, in the index 5 I have that value, and so this is not very, it's not very practical if you have something complex. And of course, this is a problem with most APIs. There is no direct mapping of complex types. It's like you have to look through a loophole if you want to access an array, for instance, in Lua, to transfer an array from Lua to C, you must traverse the entire array, getting one element by one and then projecting that single element into C. But this is really difficult. Java has some interface that you can put an array into a C form, but it's quite complex. It has problems with exactly avoiding the array being collected while you're using it in C. It's very efficient, but it's quite complex. So if you want simplicity, it's a price to pay. Oops. So conclusions. As I say, any language design involves conflicting goals, and designers must solve these conflicts, whether they are conscious or not. Sometimes they are not conscious, there is a conflict there, but of course any decision you make, you are doing something, you are preferring some directions and deferring something else. And to get simplicity in particular, we must give something, either performance, easy of use, particular features. You are always refusing to add features to the language every time. Why don't you have that? Why don't you have that? There is a lot of features that the language doesn't have. Of course, as I said in the beginning, simplicity is not an absolute goal. It's as simple as possible, but not simpler. But at the same time, it must be pursued all the time, mainly when the language evolves. It's very easy to create a very simple language, and then as the language evolves, you get more. For instance, that more or less happens with C++. It started was kind of, if you compare the original C++ description with the actual C++, is a language that is, I don't know, it's 10 times more complex than it was. It kind of exploded. And you can always argue that, of course, any single feature is necessary. Almost any single feature has real uses. But the language, the integration, the interaction among all these features sometimes is unbearable. And well, a very important lesson is that it's much easier to add a feature later than to remove a feature. So when in doubt, you should try to avoid introducing something that we are not sure. Of course, not always we did that, but we try to do. And this is also something very subtle, that it's very hard to anticipate clashes with future features. Future features, yes. Sometimes we do something that sounds very simple. Oh, that's a perfect idea. Let's put that in the language. And then 3 years later, oh, that's fun. That's something that the language must have, but we cannot put that because it doesn't match with sometimes you just remove that feature, but it's the more users you have, the more difficult it is to remove anything from even bugs sometimes is difficult to remove from the language. Yes, Microsoft knows about that a lot. So it's if possible, it's good to try to think of what we may introduce in the future, what we are thinking about. So will that feature interact nicely with something in the future? And finally, something that we followed all this time is what we call mechanisms instead of policies. A typical example is delegation. That started, people wanted object orientation, people wanted classes. Okay, what we need to provide so they can have delegation, so they can have object orientation. That's a very effective way to avoid tough decisions. You just put that, do whatever you want, so we don't have to choose. But of course, this is itself a decision. I mean, to avoid tough decisions is a decision. So, yeah. So, oops. That's it. Questions?
Why do array offsets start at 1 rather than 0?
Pardon?
Why do array offsets start at 1 rather than 0?
That's a good question. No, the array started with 1 because the language was designed in the very beginning mainly to be used by engineers, civil engineers, geologists that were used to Fortran, and in Fortran, yes, inheritance from Fortran, yes, yes. And so started with 1. And since then...
Guys fighting Fortran again.
Pardon me?
Algo guys were fighting Fortran at some point, like starting with 0.
Yeah. And then, since then, we thought that to change would be a huge incompatibility and a bad kind of incompatibility because it only shows in bugs. It would not give any kind of syntax error, compiler error, anything, just all your programs will be bugged. So it's a very huge incompatibility. And it's not that bad. That was funny that yesterday in that roundtable, one of the questions was what you love, what you most love and what you most hate about Lua. And then one guy answered that what I most hate is array starting at 1. And another guy, jokingly, but not completely joking, said what I more love is that array starting 1 is the way I think from 1 to n. And so I think most non-programmers prefer arrays starting with 1. And so when I don't buy this argument, but it's a nice argument anyway, that you can say non-programmers, they are not very good, so it's easy for them. Good programmers should not bother that much whether array starts with 1 and 0. So let's start with 1 so everybody's happy. I don't buy that argument, but it's good anyway.
So you stated that Lua is supposed to be simple and simpleness that goes small, but it's kind of keeping its small size is one of its major features, I think. It lends it to embeddability. At what point do you think, or do you think you are getting close to being done? And by done, I mean feature complete. Otherwise, or not adding any more features, because you can just keep adding features, it'll just keep growing. And you, at some point, you got to say, hey, this has reached our point, and this has reached our goal. Do you think we're there or close to there, or do you still see a lot of features are going to come in?
I think that where it is in the beginning. I think neither one nor the other. Here it is.
Yeah.
I think this is more or less what. So I think, for instance, now this graph here, I cannot read it anyway. But 501 is from 2006. So the next version would be maybe this year or next year, and still you have less than 20,000 lines. So I think we are flattening that, we are spacing the versions. So I think we are not done, but we are exactly our space. Yes, we will never reach that, but we are slowing the
Because I've been very happy with 5.1, and I saw 5.2 adding all these more things. I'm like, well, do I want to upgrade? I'm very happy with 5.1.
Yeah, but at the same time, for instance, there are some things that we can get smaller. Sometimes we remove, for instance, 5.2, we are planning to remove all the stuff about environments, which we introduced in 5.0, that it's too complex, it's too strange. And so we are changing that to a mechanism that we think it's simpler, do more or less the same thing, it's much simpler and smaller, the implementation is smaller. So sometimes you can evolve.
Evolve and not
yes,
grow.
yes, just without growing. But sometimes we grow too. I mean, we'll have more lines. We'll cross that. The barrier there is 18,000. We are going to almost 20,000, but it's a small increase.
When does concurrency occur in a Lua program?
Where?
When?
When does concurrency occur in a Lua
So I started, as I understand, as a simple program. I may create coroutines, but it's not. It's still a single-threaded model for execution of coroutines.
Yes, yes.
When does concurrency occur?
In our view, what we are trying to explore with some good results is to have multiple states. I mean, we buy the idea of processes. I always said that I don't believe any language where A equals A plus 1 is non-deterministic. I think multi-threading was introduced as an operating system concept to be used by operating system programmers. I mean, people that, and then it becomes something that everybody wants to use, everybody uses as it's something simple. I think it's almost impossible to do anything right. So mainly in a language like Lua that is to be used by many non-programmers. So I think that the concurrency in Lua should follow the model of processes communicating through some kind of message passing, mailboxes or anything like that. We have some experiments. The performance is quite reasonable, and we can do that without changing Lua. We just have a C library. You create different Lua states, and you provide those communicating functions in C. And
So one Lua state is single thread.
yes, each state is single thread, but then you can put different C threads, multi-threading in C. With one experiment we had was very interesting. You have a pool of states and an independent pool of threads, of C threads, and each one gets one state and runs that until that state's yield or ends, and so you have some tasks. And yes, inside Lua, each one, so you have processes. Each one is, from the point of view of Lua, you have processes. Each one is completely independent, and they exchange data through message passing.
You mentioned simple as possible, not simpler, and you've talked about adding and trying to subtract. What's the thing you wish you hadn't added?
My goodness. Well, one, it's easy to answer, is environments that we are removing. So that's, this one is easy. Yes.
One you can't remove.
Yeah.
It's too late to remove.
Yes,
It would have been in right around 3.2, I imagine.
Mm-hmm. Let me see. Oh, I cannot answer that. That's too dangerous. Record. That will be kept for prosperity.
Cameras off.
No, but I don't.
Off in about 2 minutes.
I'm sure I will think about something, but I cannot think about it right now. From time to time, there is some details. I know a lot of details. For instance, something stupid. It's very, very detailed, but it's completely stupid. Is that you can have multi-lines in a string, in a literal string. You have multi-lines. You have a backslash, end of line, like in C, but then you have the end of line there. In C, you must put a backslash and the backslash to change lines. And when I saw that, I thought, that's stupid. If you want to change lines, just change lines. But that's not stupid at all. Sometimes you want a huge string without line breaks, but you need the line breaks to format your program. So this is an example that's something that, but again, we could change, but it's exactly that kind of change that it doesn't pay to. I mean, it's a lot of noise for a small thing. So.
I have a question regarding influence on Lua and what might Lua have influence.
Mm-hmm.
So obviously you cited a lot of influence from Scheme.
Yes.
That shows, right? But if there are any languages that to you feel, close to Lua, that, you feel capture ideas in the same spirit that Lua does, what would those languages be? And I'm specifically interested in one language that came out very recently, if you had, had time to experiment with it, Go from Google.
Oh no, I haven't time
okay.
I haven't had time
even
to try
regardless
it.
of Go, what languages would you feel are close to Lua in that sense?
There's one, of course, Scheme. Another, in some very strange ways, is Tico. I think Tico was the first language, and it really deserves all the merit of the first language of being created for scripting. This idea of the language, the API, it's actually a library, it's an API. I think that the main problem with Tico is exactly that they put so much attention to the API, they forgot the language itself. So, but I mean, the main idea of scripting.
Language in the first place.
Yeah.
Remember they said to help the VLSI effort, and then in hindsight it was useful, and so it spread.
Yes, but I think that idea of scripting in that sense of a language to control other parts written in C, etc., that came from Tico and was a big influence for us. When we started thinking about Lua, we saw Tico, we saw, oh, that's a great idea, but exactly, that's not a language that civil engineers or geologists could use with all those codes and extra codes, etc. So it was a very big influence.
You said civil engineers at least 5 times. It's sort of odd that computer scientists thinking about civil engineering problems. Why civil engineers? Why did that?
Because Lua was created to be used by the Brazilian oil company.
Okay.
It was a partnership between PUC. That's something also important. Lua was not created as an academic language. It was created inside the university, but we were developing software for the Brazilian oil company. And so, and the users, our users, were people from the oil company. So that's why I talk about civil engineers and geologists and mechanical engineers. I forgot mechanical engineers too, but so that people that work with a lot of programs, they use the programs, and Lua was created exactly so they could configure those programs. So the language should be easy for them to use.
So you had users before you had a language.
Yes, that was very important, yes.
Installed base, would you say that you have more petroleum engineers as users now than you do game studio programmers?
Pardon me?
Which installed base would you say is larger now? The petroleum engineers or the gamers?
All gamers,
Game
much
programmers.
bigger. But gamers have the same thing, because a lot of people that use Lua in the game studios are designers. I mean, game artists. For instance, yesterday they were talking about even audio designers, the designer people that create the audio for the game. They are using Lua, they are programming in Lua. So I think you have more or less the same situation with games. People, the real programmers, they create the engines and they create the interface so Lua can access the engine. And then the game designer that will create the story, that create the lines, etc., they use Lua to program the game. So in games we have more or less, they are far from civil engineers, but they are non-professional programmers. And
Actually, worked with.
so, sorry.
Sorry.
What are some examples of the dark corners of the C language that different compilers?
The conversion of, I don't remember exactly the order, but if I remember correctly, the conversion from an assigned char to an unsigned int. You can first convert the assigned char to a signed int and then to an unsigned int, or you first convert the signed char to an unsigned char and then to an unsigned int, and you have different results. The standards say the result must be 1, but we found compilers that did the other way, and most of people don't even care, because most people don't know which is the correct order, so nobody complains about that. So this is an example of dark corner. So when we have that thing, we just put explicit casts all the way along. We do not never convert a char to an unsigned int. You first convert it to an unsigned char, for instance, and then you convert. This is an example. There are the reverse examples. That is problems that are correct, but people don't know what is correct. For instance, it's very common people to do something like a loop, decrementing a pointer until it arrives in the beginning of the array. And so usually, depending how you do the loop, you pass 1 behind the beginning of the array, and then you compare, oh, this pointer is smaller than that one, so you stop the loop. But the standard does not assure that will occur. I mean, we did have problems with that, some machines that allocate with segmentation. So the segment, the array starts exactly at the beginning of the segment. So when you pass 1 here, you just goes around and it's large. The loop never stops. Another very common mistake is to do like the C-type library. You do like is alpha of a char. Everybody does that all the time. You have a string. And then you do is alpha star S. You check whether a char is alphabetical. And this is wrong, because the is char only accepts positive numbers. So if your char type is signed, you cannot use is alpha or is digit or anything like that over a char. You must first convert it to an unsigned char and then to. So this is another example. This is the dark corners that we will not avoid from that point of view. I mean, we do not have problems with the compiler. We have problems with the code. We must have, because a lot of compilers are complacent. Is that word? Complacent about those errors. So, for instance, a lot of compilers, not in that case, not the compiler, the libraries accept negative indices, so you do not have errors. It's wrong, your code, but it runs correctly in a lot of systems. And then you hit a system, and then you start complaining, oh, that system is crazy. And then, oh, that system is correct. All the others are accepting wrong code. That happened a lot too.
To get back, I work with people in the oil industry and help them get into parallel computing, whatever. Now they're finding with the multi-core issue. I'm not saying there's any. People in Brazil use it for high-end computing that involves multiple processors and multi-cores. Does it help in that context?
Sorry, what helps?
Lua.
If Lua helps.
Yes. We talked a little earlier about parallel.
Yes, but POVS, as I said, we are starting using that, so we have some experiments, but I don't think people are using still Lua, I mean, heavily in parallel contexts. Usually what's very common is that you have Lua controlling other, so you have parallel tasks. For instance, that would, this is a real example. We had one robot of a long time ago. It was multiprocessed. It has one main processor and different small processors to control some mechanics. And so it runs Lua only in the main processor, and the other processors run C. It's just specific C code, and then the main processor controls these other applications. And as I said, this guy from Sony, he was discussing using Lua in the SPE, in the Bell, the cell processor. But again, he said, I don't know why people would like to use Lua on those other processors. The common architecture should be to use Lua in the main one, and it controls. So I think there is a lot of parallelism you can explore without Lua being parallel. But we are exploring these ideas of doing Lua parallel.
MPI instead of using MPI.
MPI, yes. No, MPI is too heavy. But
Yeah,
but the idea, yes, the idea of message passing.
As Lua instead of, because now it's multi-core. There's a big, that whole question comes back up.
Yes.
Then we need lightweight MPI or whatever.
Yes.
Lua, your lightweight MPI.
Yeah, we hope so, but we still have to prove it.
My question specifically to, you brought it up on a slide as a set of problems with the Lua and C API, the concept of the stack being used to pass parameters between the two worlds. It's also at the same time, as you mentioned earlier, an elegant way to solve some of the problems with keeping track of what objects can and can't be collected across that. Where did the inspiration for that specific concept come from?
From the stack?
In terms of it being used as the way to transfer between the two. And also, like...
In particular, for us, this idea came from a very strange way. It came from the implementation. This was very strange, because Lua, now it uses a register-based API, virtual machine, but in the beginning it used a stack-based virtual machine, like most virtual machines. So the API, in the beginning, it was a kind of, it tried to disguise the stack in the back. And so what we realized that if you expose the stack would be much easier because, so the idea came from here. Of course, we do not expose the real stack, etc. But so what people, we try to do, so you create, in the beginning, until I think version 3.1, something like that, we did have Lua objects, but when you created a Lua object, that object was in the stack, but then we kind of avoid people, we change the indexes so you could not access that. It was a real complications. So it's much easier, and people, it's funny because exactly a lot of people complained in the beginning because the stack is it's much easier to use the Lua object. But the point is that people did not have, I mean, it's easy when you do not understand exactly what you are doing. So it's very easy. Just do it, or you do it, it does it, and you do it and it works, and that's okay. But when you start to having any kind of problems, they didn't have a clear model what was going on, so it was almost impossible to debug. And with the API, it's a little more difficult, but then you have a very clear model what's going on, and anytime you can print what is in the stack, and so you know what it's, I mean, it's much more concrete, the API. It's much more less abstract, and so it's much easier to explain, to understand. So now people know what they are doing. I think that's why it's more difficult, because they must know what they are doing.
I think as you pointed out, though, the real programmers are the ones interacting with the stack. The people who are using Lua aren't seeing the C API. So
yes, exactly.
It's not that big of a deal.
Yes, that's for sure is an important point. Yeah. It's a completely different hat you use when you are programming the API. Or other question?
One more question. So I think I understand most of the choices that you made as far as syntax of the Lua is concerned, and some of the choices were very clearly explained in the articles that you published. But there is one choice that I don't fully understand, so maybe you could help me. So where did the colon syntax for at least calling methods come from? So why not something like arrow or something more similar to other ways of calling methods?
I just have that. You can keep talking. I just want to hear my.
okay. I don't know.